Welcome to the second video on X-rays as part of the A-level medical physics option. In the last video we talked about the X-ray tube, and if you haven't seen that video you should watch it first. This video talks about the production of X-rays in the X-ray tube, and it also talks about the distribution of energies of the produced X-rays and the origin of those X-rays. Okay, so let's get going. Alright, so the electrons in the X-ray tube are accelerated by a large potential difference, and they hit a target anode, which is made normally of tungsten. Now there are two mechanisms going on inside the target anode, inside the atomic structure of that metal. And these produce X-rays of two different types. The first type of X-rays produced are called breaking X-rays, sometimes known as Bremsstrahlung radiation. The second type of X-rays produced are called characteristic X-rays, and we're going to have a look at each of these in turn and find out what the origin of these two is and what the mechanism is. Now over here we've got a little graph of intensity, so that's the intensity of the X-rays produced against their energy, and now the energy here is measured in kilo electron volts. So you can see that there's this typical continuous distribution of X-rays, all right, which depends the height of which and the spread of which depends on the accelerating voltage. Superimposed on that, you can see these spikes. All right, now these spikes are individual frequencies of X-rays, individual energies of X-rays produced. All right, now the breaking X-rays, which we'll talk about in a moment, produce the characteristic, or rather the typical, I shouldn't say characteristic because that's what the other ones are called, the typical smooth continuous distribution. The characteristic X-rays form these spikes. Alright, so the breaking X-rays form the smooth distribution, the characteristic X-rays form the spikes. Okay, so let's have a look at each of them in turn and try and figure out what's going on. Alright, so an electron can be incident on the tungsten anode, alright, and actually penetrate the material. And as it does so, it will, some of them at least, will come across the nuclei of the target atoms. So this is usually made of tungsten. Alright, so this one is a nucleus or an atom of tungsten. Obviously this has got a very large positive charge, and the electron has a negative charge. So the two of them will interact electrostatically, and that will result in a change of trajectory of the electron as it approaches and passes the tungsten atom. Alright, in effect what we have is a deceleration of the electron. Right, the electron slows down. Now initially the electron had a certain amount of kinetic energy, here called EK initial, right, the initial kinetic energy. As it passes the tungsten atom and is decelerated, it will lose a certain amount of kinetic energy, the change in kinetic energy denoted here by delta EK. So what happens to that kinetic energy that the electron has lost? Well, it's given off as a photon. Alright, there is an interaction with the electric field, and as the thing decelerates, a photon is given off. And in fact, all charged particles, when they are in electric fields and decelerated, will emit electromagnetic radiation. Okay, now it just so happens that the amount of deceleration here causes a photon to be given off whose frequency is in the X-ray range. Alright, so the X-ray is the type of photon produced when this amount of kinetic energy is lost, alright, as it interferes with these atoms. That's one of the reasons why they make these targets out of tungstens. Okay, so that's the first mechanism, and that's what produces the breaking radiation. Second mechanism is, as we say, called characteristic X-rays. Now this is an entirely different mechanism for producing X-rays. And what happens in this particular situation is the electron will be incident at this angle, for instance, and what it will do is it will ionize one of the tungsten atoms, all right? But it will pass close to the nucleus, deep within the atom, and it will actually ionize sometimes from the lowest shell. Now, for historical reasons, this is actually sometimes called the K shell. All right, the other shells you can see are given different letters. The K shell is usually called the ground state or the lowest energy level, but in this particular case we're calling it the K shell. So what happens is the electron from the K shell is emitted from the atom, ejected from the atom by the incident electron, so both of them zoom off in different directions. This leaves a gap, an empty space in the K shell. And then what happens is spontaneously one of the electrons from the outer shells will transition downwards into the K shell to take the place of the ejected electron, which is not there anymore. And as it does so, it will travel from an energy shell with energy E2 down to to the K shell, which has, for example, energy E1. And the difference in those energy levels that the electron loses, we call it delta E, is equal to the photon energy that is given off. Now, if you remember your quantum mechanics last year when we were looking at atomic spectra, you'll remember that when an electron transitions out, inwards into a lower energy level within an atom, a photon is given off. For energy transitions into the K shell, that photon energy is in the X-ray spectrum. Okay, so that's why we're interested in them. So ionizations that occur in the K shell are followed by inward transitions into the K shell, resulting in the production of an X-ray photon with energy HF, all right, which is equal to the difference in the two energy levels. Okay, so let's go back to the curve that we saw of intensity against energy and have a look at that. Now, one of the main things to notice about breaking radiation is it can take pretty much any value, or certainly a range of values, because, and actually we need to go back to the slide that we were looking at before for that. The deceleration of the atom, of the electron as it comes close to the atom, can effectively take any value. You know, the electrons will be incident upon the material at various distances from the nucleus, and therefore they'll be decelerated by different amounts. And in fact, there's a continuum of amounts of deceleration. The amount of energy that's lost by the electron forms a continuous spectrum, all right, and therefore the X-rays produced also form a continuous spectrum. So the breaking X-rays produce this characteristic, sorry I said it again, this typical curve, okay, that is the one that's produced by the breaking radiation. The characteristic X-rays, because they are quantized effectively, because the electrons can only fall in from these, or transition inwards from these outer shells, right, that is going to have discrete values, all right. The energies produced here have discrete values because we're moving from one energy shell to the other, and so that's why you get individual frequencies produced, and each of these spikes corresponds to a different transition downwards into the K shell. Alright, so this will be from one energy level down to the K shell, and this will be from another energy level down into the K shell. Alright, so the K shell ionization transitions result in these spikes, and the breaking radiation results in this continuous spectrum because it can have effectively any value. Okay, and that's it.